Welcome to Cookie's Maths and Science Hub. In today's video, we're exploring the concept of circuits. So you've probably heard about circuits before and thought of electrical wires and other such matters. But in the context of physics, a circuit refers only to a closed loop or path through which an electrical current can flow. It involves the interconnected components that facilitate the movement of charged particles, most commonly with electrons when we discuss in physics, within a conducting material. And our physics is used to explore the principles governing the behavior of electrical circuits and their components. The diagram on the right shows a basic circuit with a few components we're going to discuss. We have a resistor, which we'll go into more specific detail shortly. We have a power source, which could be a battery, for example. And then the two things that are unique to this diagram are the measuring tools we use, which you'll need to be familiar with for drawing them on circuit diagrams. We have the ammeter, which measures current, and the voltmeter, which measures voltage. The two key things to remember with these ones is your ammeter is connected in what we call series. That is, you can see the circuit passes through it, whereas a voltmeter is connected in what we call parallel, which is where it's connected to the circuit rather than the circuit passing through it. You can see it's connected on either side of the resistor. This will measure the volts across that resistor. Let's go into more specific detail about some of these terms now to help us as we move further into our discussion on circuits. But before we explore some different concepts, let's make sure we're familiar with our three key terms that we're going to be discussing. There is voltage, also known as electric potential difference. And this is the measure of electric potential energy per unit charge in a circuit. It is given the symbol V, and it has the units volts, represented by V. Voltage provides the driving force for the flow of electrical charge in a circuit. It is analogous to the pressure in a water pipe and is responsible for the flow of electric current, which leads us straight into current, which is the flow of electric charge per unit time. It's given the symbol I and has the unit amps or amperes, given by the letter A. Current is the rate of flow of electric charge through a conductor. In a closed circuit, it is the movement of electrons in response to the applied voltage. Finally, we have our resistors. Resistors are electrical components that introduce resistance to the flow of electric current in a circuit, as the name would suggest. They're given the symbol R, and they're measured in ohms, with the ohms symbol shown there. Resistors regulate the flow of current and are used to control the voltage and current levels in a circuit. They dissipate electrical energy in the form of heat. For example, a light bulb is considered a resistor, as it resists that flow of current and gives off other energy. We can relate these three concepts using Ohm's law. That is, it is found through certain devices that the current flowing through them is directly proportional to the potential difference placed across it. That is, current is proportional to voltage, which gives us Ohm's law. We can use this to find the equation voltage is equal to current multiplied by resistance, which we can use to solve for problems where ohmic resistors are present. Now, there's also non-ohmic resistors. Now, the key thing I want you to remember here is that if you were to plot them both on graphs, as we're shown in these images on the right, an ohmic resistor gives a straight line gradient for current versus voltage, whereas non-ohmic resistors give a curve. We say resistors are in series when they are connected to end, as shown in the image below. In this case, we can find the total resistance by simply adding up the resistance of each individual resistor. For these scenarios, the voltage, or the potential difference supplied to the circuit, is the sum of the potential difference across each resistor. The current, on the other hand, is the same across the board. So the total current equals the current at any point throughout that circuit. Let's look at a simple problem now dealing with a series circuit. So we're asked to consider the circuit to the right. If the total resistance is 20 ohms, we're told to find the current flowing through the circuit and the resistance of the X resistor. If you look at our image, we have one resistor of 2 ohms, another of 14 ohms, and one with an unknown amount. So for this, we can use V equals IR, and we can rearrange that formula to give us I equals VR, or current equals voltage over resistance, which is going to give us 8 divided by 20, which is going to give us 0.4 amps. Remembering it's important to include the units. To find the resistance of our X resistor, we're going to have R total is equal to R1 plus R2 plus R3, as there are 3 resistors in this case. which is just going to give us 20 is equal to 14 plus 2 plus x. And hopefully you can easily see there that our x is going to equal 4 ohms. We're next asked to draw an ammeter and voltmeter to measure the current and voltage traveling through our X resistor. So you need to remember from our diagrams that an ammeter and also that our current is going to be the same anywhere we put that ammeter in a series circuit. So our ammeter is going to be placed in series. You can see the circuit passes directly through the ammeter, whereas our voltmeter is going to be placed in parallel. That is, it connects to either side of the resistor to measure the potential difference across that resistor. In contrast to connecting the resistors in series, we can also connect them in parallel, which is where they are stacked on top of each other as shown in the image, as they are connected in parallel to one another. In this case, it turns out that we actually need to add up the current through each resistor to get the total circuit current. However, the voltage is the same in every part of the circuit. This is why in household circuits, we have things connected in parallel, which is why the lights don't dim when you have the fridge turned on and other such matters, because the voltage remains the same across the entire system. To find the total resistance, it's a little trickier in these systems, as you can use the following relationship. 1 over RT, or 1 over the total resistance, equals 1 over R1 plus 1 over R2, etc., including more resistors. If you only have 2 resistors, this simplifies down to the formula resistance total equals R1 multiplied by R2 divided by R1 plus R2, which is what we'll use in a problem now to demonstrate this formula. So as you can see, if we're asked to find the total resistance of the circuit to the right, which has a 2 ohm resistor and a 14 ohm resistor connected in parallel, we can use the RT equals R1 R2 over R1 plus R2 formula, which gives us 2 multiplied by 14 over 2 plus 14, which gives us 1.75 ohms.